the mechanism of conduction in polyester by using reductive doping, right? So reductive doping, that is by treating with an reducing agent, that is electron donor, right? So first of all, let us write this polyester structure like this, right? So you can write the alternative single and double bonds here. Okay, so it is having linear structure which is a rigid chain and consisting of continuous conjugation. So as it is reductive doping, so we have to introduce negative charges, right, by using reducing agents, right, that is proton electron donors, right? So here in this case we are going to take an electron donor such as sodium naphthalide, right? Sodium naphthalide electron donor, we are going to take it in THF, that is tetrahydrofuran. Lithium naphthalide also you can take. So what happens if you are treating this neutral polymer chain, so with a strong reducing agent or electron donor such as sodium naphthalide, it will introduce one of the electron into the polymer backbone chain, right? So here as it is introduced, so these two electrons will shift to this side, and this electron will be added on the one of the carbon atom, right? So electron will be added by this, right? So that can be written like this. So now, so what happens when you are doing reduction, right, treating with a reducing agent, it will add an electron. So these electrons will come out and form a negative charge here, right, and this free electron will form a radical, right? So this particular state is called as polar, right? As two charges are there, so one is positive charge, the other one is this one, so this is called as, it is a neutral polyester, right, and this is a polar ion will be formed, right? And second reduction, right, and second reduction, so it is going to introduce one more electron into this, so that will be added here, and thereby it is going to form bipolar ions, right? A bipolar ion will be formed on second reduction, right? So that can be written like this. Right, so you can take, so if you come here, so this will remain as it is, and so this bond will be, these electrons will be shifted here, and it is going to form negative charge, and this one more electron will be coming over this side, and this is called as bipolar ion, right? So bipolar ion will be formed. So next, these bipolar ions will undergo rearrangement, thereby they are going to establish back one of the double bond, and as a result of which, so this is rearrangement, so as a result of which, so we are going to get, so negative charge, right, and that negative charge is compensated by sodium ions, and that is going to form a soliton pair. So if you apply potential, these soliton pairs are going to move in the opposite direction towards the electrodes, so as a result of which the material will start to conduct electricity. That can be written like this. Right, so this negatively, so this electron, similarly it is going to form an a double bond, establish back a double bond, right? This negative charge is compensated by positively charged Na plus ions, and double bond will be formed here, and this is Na plus will be compensated, and this will be there as it is, right? This is called as soliton pair. So if you apply potential, so these will start to migrate towards opposite electrodes, and thereby they will start to conduct electricity, right? So if you write an energy level bands for this, so as similar to that of previous explanation, so this is a valence band and this is a conduction band, right? So after doing the reduction with an reducing agent, then what happens? So it is going to introduce, one electron into the matrix, and at the same time it will remove these pi electrons, right? These two electrons from the valence band, and it will create an intermediate energy level. So that's why, so these two electrons, earlier it was there in the valence band, will come out, right, like this. They will come out like this, and one more electron will be retained here, right? One more electron, this electron will be a lone free electron will be there here. So if you come to bipolar ion, in this case what happens? So as we are adding doing reduction for the second time, this is a conduction band, this is so valence band. So two electrons are there, and you are adding, you are doing the reduction for the second time, so you are adding one more electron that will come and form here, right? So this is called as bipolar ion, right? So then in the soliton pair, so it is going to form the energy band of equal range, right? All the electrons are of equal energy range, right? So like this. So this is a soliton pair. So that's already we have written in this case. So in this way, by reductive doping, it is possible to convert an organic polymer into conducting polymer, right? So here the majority charge carriers are electrons, right? So that's why it is called as N doping. Whereas in the earlier case it was P doping, because majority charge carriers are holes, right? Here, so these negatively charged electrons are compensated by positive charge Na plus ions. So that's why polymer as a whole appears electrically neutral, but it will conduct electricity. If you apply potential, these solitons will start to move towards opposite electrodes, right? So in the opposite directions. So this is what the mechanism. Yes, if you see the applications of this polyacetylene, right? So these polyacetylene, applications of polyacetylene. These polyacetylene materials so can be used as an electrode material in rechargeable batteries. Say for example lead acid batteries, they are used in making sensors for pH, oxygen, SO2, ammonia and glucose, right? So they are used in telecommunications. So they are used in the making of electronic items such as transistors and diode, and they are also used in fuel cells as an electroactive materials, right? So these are the applications. The next concept is graphene oxide. So before going to this graphene oxide, let me tell from where we are going to get graphene, right? So what is graphene, right? So graphene is a single atom thick layer of carbon atoms which are taken out from the graphite, right? So then what is graphite? Graphite no doubt is an allotropic form of carbon atom. So it is a three-dimensional material made up of millions of graphene layers stacked together one after the another, right? So here our aim is to take out one atom layer of the carbon atoms from that graphite, so that we are going to get graphene, right? So graphene is a two-dimensional nanosheet, right, having one atom thick layer of carbon atom, right? So why it is called as one atom thick layer of carbon atom is equal to the thickness equal to the single carbon atom is, if you look at from any side, so it will look one atom thick carbon atom. So either you can look from top or from the side view, it will look like one atom thick layer of this one, carbon atom. So that's why it is called as two-dimensional one atom thick layer of graphite, right? So that is the thing. So this graphene is 1 million times thinner than that of paper, normal paper, right? So if you can take, this is the graphene oxide, or this is only one material, nanomaterial, which is having only surface, right? So only surface. So this graphene oxide or graphene is the mother of all the materials, all other nanomaterials like carbon nanotubes or fullerenes. So if you take out one single sheet of carbon atoms, one single sheet of carbon atoms from that graphite, and if you roll together in the form of a cylinder, it is called as single wide carbon nanotubes. If you are taken multiple graphene sheets, right, and if you are rolled together in the form of a cylinder, you are going to get multi-wide carbon nanotubes. So likewise, the same graphene sheet, if you are if you prepare in the form of cylindrical or ball shape, so then you are getting it a fullerene. So that's why it is called as the mother of all the other forms of materials, that is carbon based materials, right? So then if you come to this graphene oxide, so the graphene oxide is the one which consisting of, if you are going to treat this graphene with various functional groups that consisting of hydroxyl group, epoxide groups, carbonyl groups or carboxylic acid groups, right, then it is going to become graphene oxide, right? It is going to become graphene oxide. So then graphene oxide consisting of hydroxyl groups, carbonyl groups, alkoxy groups, carboxylic acid groups, so etc., right? That is called as graphene oxide. So here our aim is to take out one layer of carbon atoms, right, one sheet of carbon atom from this graphite, right, in order to form graphene. So before going to prepare graphene, we will get graphene oxide, right? So here first, in order to prepare graphene oxide, we are going to follow modified Ammer's method, right? So we are going to follow modified Ammer's method for the preparation of graphene oxide, right? So here we have taken graphite sheet, and this in the modified Ammer's method of preparing graphene, it consisting of two steps. So one is oxidation step. The first step is oxidation. So our aim is to prepare take out one atom thick layer of these carbon atoms from this graphite, and we have to separate it, and that is called as graphene, right? So that's why first you have to do the oxidation, right? The first step involved in this preparation is oxidation. So if you oxidize this graphite using a strong oxidizing agent like KMnO4 in presence of sulfuric acid and by taking sodium nitrate, so what happens, some of the carbon atoms in this graphite layer are oxidized, right? Some of the carbon atoms are oxidized, and they are going to convert that into carboxylic acid groups or hydroxyl groups and other things, so like this, right? And this sodium nitrate, the sodium ions as well as nitrate ions are going to stack between the layers, right? So here graphite is it is a three-dimensional material consisting of millions of graphene layers stacked one after the another, right? There are n number of graphene layers are joined together, thereby they form graphite. So here we need to take one single sheet of carbon atoms from this. So to do that, first step is oxidation. So what happens, there are so many graphene sheets are there, right? Carbon atom sheets are there here. So if you are treating with this, the sodium ions as well as nitrate ions are going to stack between the layers, so that it will help us to separate the sheet, and this KMnO4 go into that layer, as a result of which, and it will oxidize some of the carbon atoms, right? So these some of the carbon atoms, so whatever the product we are going to get, that is called as graphitic oxide, right? So that graphitic oxide, if you further treat with water, and if you subject it to ultrasonication, you are going to get graphene oxide, right? The graphene oxide that consisting of so many oxygen containing functional groups like hydroxylic acid groups, like COH group, like epoxy group, like carbonyl group, C double bond O group. So that particular compound is called as graphene oxide, right? So that is called as graphene oxide. So if you want to prepare graphene from this graphene oxide, you have to further continue this step, right? So anyhow it is not there in your syllabus, so I am not going to explain that. So for your convenience I will tell you. So if you want to prepare graphene from this graphene oxide, so in the graphene oxide, so what happens after doing after treating with water and ultrasonification, so the layers are separated, right? But some of the carbon atoms are oxidized. They're consisting of various functional groups like this, right? So then that graphene oxide is subjected to reduction in the second step using sodium borohydride as a reducing agent. Then we are going to get a single sheet of graphene, right, carbon atoms, and that is two-dimensional graphene sheet, right, which is taken successfully out of this graphite. Okay, so this is what it is called as the synthesis of graphene oxide, right? So you can limit your explanation toward up to graphene oxide. It is sufficient, right? So as I said, this graphene oxide is a mother of almost all the materials, carbon based materials. So then definitely it has some very good properties, right? So graphene oxide. So now let us see the properties of graphene oxide. So if you can see the properties, the first property is it is hydrophilic in nature, right? So why? Because as it consisting of so many oxygen containing functional groups, right? So it is hydrophilic in nature, like it consisting of hydroxyl group, carbonyl group, carboxylic acid groups, epoxide groups, alkoxy groups, etc. That's why it is hydrophilic in nature, right? And the second property is it can mix with matrix such as polymer or ceramics and make their properties like mechanical and electrical properties more, right? So that is the second property. And if we come to third property, it is hygroscopic in nature. Why? And therefore it can react with it can form a hydrogen bond by reacting with water molecules, right? And the next property is it is having large surface area, so that's why it is more reactive, right? And the next one is it is having low thermal conductivity compared to graphite, and it is having low electrical conductivity than graphene, right? So these are all the properties of this graphene oxide, right? These are the properties of the graphene oxide, right? So while going to prepare a graphene, we are going to get graphene oxide, remember. So our aim is to take out one atom thick layer of these graphene carbon atoms from out of this graphite. It is a two-dimensional nano sheet, right, with a thickness equal to one single carbon atom, remember. So now coming to the applications, as it is very a thin sheet of two-dimensional nano sheet, right, definitely. So similar to as the size reduces, definitely it is going to exhibit lot of applications, right? So if you look at the applications, this graphene oxide can be used in coating technologies because its films can be easily deposited on any substrates like aluminum or steel, etc. So this is the reason you can use it in the coating technology. And second one is graphene oxide papers can be used in desalination techniques as well as reverse osmosis techniques in order to treat water or pure water from the saline water, right? So there is a second applications of this graphene oxide. So coming to the third one, GO can be used in the medical field such as for targeted drug delivery, for cancer therapy, for bioimaging, and in the biosensors, right? Because of its biocompatibility nature. So similarly, these nanocomposites of GO and silver can be used for bacteria detection, right? And at last, these GO can be used as a biosensor for detection of the cancer in the early stage, right? Detection of the cancer in the early stage. So these are all the applications. Okay, so this is all about graphene oxide and its synthesis by modified Ummer's method, right? As I said, it consisting of two steps. First step is oxidation, you are using KMnO4. The second step is reduction if you want to prepare graphene, right? Here we are limiting our explanation to graphene oxide, right? So that's why, so only one step is sufficient. So if you oxidize using all these things, so all these layers, see imagine this is one layer, right, of a carbon atom. Likewise imagine one more layer, likewise imagine one more layer, like that the atoms are stacked, right, one after the other. So we have to remove one atom out of this. So that can be done by oxidation by using these functional groups, and then substituting to ultrasonification by treating with water, you will get so this graphene oxide, and then if you subject to reduction you will get graphene, right? So this is what the explanation.